Here we have two tiny spherical water drops that both have the same charge, -1 times 10 to the -16th power coulombs, and the distance between their centers is 1 centimeter, or 1 times 10 to the -2 meters. Part A of the problem asks us for the magnitude of the electrostatic force acting between them. Finding the electrostatic force between two particles is simply a matter of applying Coulomb's law, so let's go ahead and use that formula here. And simply plugging in our values gets us an electrostatic force of 8.99 times 10 to the -19th power newtons. Part B of the problem asks us to find the number of excess electrons that each drop would need to have in order for this charge imbalance to exist in the water drops. The important physics concept to remember here is the fact that any charge is quantized so that it is an integer multiple of E, the elementary charge. This means that any charge, Q, for instance, can be represented as the elementary charge, E, times N, where N is the integer multiple of the elementary charges that are included in the total larger charge. Now, the elementary charge really refers to the magnitude of the charge in a single proton or electron, meaning that we represent E as positive in a proton or negative in an electron. Since we're dealing with electrons here, this E should be negative, so we'll add a little negative sign on the outside of the formula. Now, since we're looking for the number of electrons, or N, let's divide both sides of this by -E to get N on its own. Now let's plug in the actual value for the elementary charge, or 1.6 times 10 to the power of -19 coulombs, along with the charge we're given by the problem for one drop of water, which is negative, incidentally, so the negatives cancel out. As we can see here, we end up with an answer of exactly 625 electrons.